Hello Sleepy Science subscribers, welcome back to the channel tonight. Thank you for being here. Before we begin, please remember to subscribe and leave a like so more people can drift into this gentle calm with us. And as always, I'm truly curious about where you're watching from and what time it is for you right now. So feel free to share it in the comments. Your messages float through this space beautifully and help soften the quiet horizon we share together. Now, let us ease into tonight's slow, dreamy journey. In the dim light of a quiet evening, when the world begins to fade into stillness, there is a gentle comfort in wondering about things far smaller than we can see. Time, for example, something we feel, something we measure, something that seems to drift forward endlessly, behaves in ways more delicate and strange when we look deeply, all the way down to the level of atoms. If you listen closely to the silence between seconds, you may sense the subtle rhythm that guides every event in the universe. On the atomic scale, this rhythm softens, becoming less of a ticking clock and more of a shimmering field of possibilities. Time does not march here. It floats, it stretches, it folds into itself, like gentle waves rolling under a quiet horizon. To understand the flow of atomic time, we must imagine a world so small that ordinary rules fade away. Atoms do not experience time in the way we do. They do not age. They do not remember. They exist in a kind of deeper calm, where the movement of particles is guided by probability rather than certainty. Quantum mechanics shows us that at this tiny scale, time becomes subtle. Instead of a straight line, it becomes a soft landscape in which particles drift between states. An electron, for instance, does not simply orbit a nucleus. It exists in several possible positions at once, as if floating in a delicate cloud. Only when we observe it does the cloud collapse into one place. That collapse is a moment of time. A transition, a shift, a gentle settling of what was once uncertain. And so, as we begin this long and soothing journey into the heart of the quantum world, notice how your breath slows, how your thoughts drift in gentler directions. The universe beneath our feet, beneath our cells, beneath every atom, moves with a quiet grace that invites you to sink into deeper calm. For in the realm of the very small, time is not just something that passes. It is something that emerges, softly, silently, endlessly. As we move a little deeper into the atomic landscape, the familiar idea of time continues to soften, stretching into something more fluid than the ticking rhythm we live by. Inside an atom, the world feels quieter, wrapped in dim light, where moments drift rather than march, fading softly into one another like gentle waves sliding across a silent shore. Here, the behavior of particles does not simply unfold in time. Instead, time itself seems to emerge from the delicate transitions between states. The nucleus, dense and compact, holds protons and neutrons bound together by the strong force, a force so powerful that human language barely captures its intensity. Yet at this tiny scale, even such immense strength feels strangely calm. Protons are not fixed spheres, but dynamic clusters of quarks weaving in constant shimmer, each quark flickering between energies, each gluon drifting into and out of existence. These inner fluctuations unfold within intervals so fleeting that the very meaning of before and after begins to fade. Time, in this restless core, becomes a pattern of change rather than a flow. Meanwhile, the electrons surrounding the nucleus do not orbit like planets circling a star. They float in regions defined only by probability, existing in blurred shapes that resemble soft clouds of possibility. When an electron shifts from one energy level to another, that shift is not a movement through space, but a leap, sudden, quiet, and without a visible path. These quantum jumps form some of the universe's most fundamental moments, tiny pulses that structure the flow of atomic time. Each transition marks a gentle step forward, a subtle reorganization of the possible into the actual. In this soft and uncertain domain, the concept of time becomes tied to change itself. A particle vibrating at a certain frequency defines its own internal clock. A cesium atom, for example, vibrates with such perfect regularity that we use it to measure seconds. But even this regularity is not the steady heartbeat it appears to be. Beneath it lies a sea of quantum fluctuations, each one drifting gently beneath the quiet horizon of what we can observe. Every vibration carries a signature of order, yet within that order lies a flicker of unpredictability, a reminder that the flow of time at this level is never rigid. As these vibrations continue, as electrons fade into new states and quarks dance within their confined space, the microscopic definition of time becomes clearer. Time is not a separate river flowing outside events. It is the harmony created by all these tiny transitions. The universe does not keep time. It is time, emerging from the changes happening moment by moment in the smallest spaces imaginable. In this deeper calm, as the atomic world reveals its rhythms, one realizes that time on this level is not measured. It is felt in quiet pulses that drift beneath the structure of everything. As we continue descending into the quiet inner world of atoms, the flow of time becomes even harder to separate from the motions that create it. At the quantum level, nothing simply moves the way we imagine. Instead, events unfold in soft transitions, in delicate probabilities that drift and shift under a faint, almost invisible rhythm. It is within these transitions that time gains its texture, like gentle waves rising and fading across a quiet horizon. Electrons, for instance, do not travel along defined paths. They linger in regions of possibility, forming shapes that resemble rings, shells, or clouds that float around the nucleus in silence. These shapes are not physical objects. They are mathematical descriptions of where the electron might be. When the electron changes energy levels, the shift is abrupt but gentle, like a soft flicker in dim light. This flicker, the moment the electron releases or absorbs energy, marks a tiny pulse of atomic time. These pulses, when viewed collectively across trillions of atoms, create the steady rhythms we use to measure seconds and minutes. Yet beneath that steady surface lies a sea of fluctuations. Each electron's transition contains uncertainty, a slight drift in timing that softens the perfect regularity we imagine. Even the atomic clocks we rely on, those built from the vibrations of cesium or ytterbium, operate within this shimmering realm where time flows from probability rather than certainty. The second they define is astonishingly stable, but never perfectly so. The universe always leaves room for slight variations. Meanwhile, inside the nucleus, quarks and gluons move in a chaotic swirl, a storm so rapid and complex that time behaves almost like a blurred sketch. These particles do not follow smooth paths. Instead, they flicker into existence, interact, fade away, then reappear in patterns governed by the strong force. Every flicker is a tiny register of time's passage, yet the intervals are so brief, so fleeting, that they lie outside anything we can directly sense. In this region, time feels more like texture than flow, less like a line, more like a vibration. At an even deeper level, the idea of before and after becomes increasingly difficult to define. A particle may exist in multiple states at once, drifting across overlapping possibilities. Only when it interacts with the environment, only when a measurement collapses these possibilities, does a single outcome emerge, creating a tiny anchor point in time. That anchor is a moment. That moment is time solidifying for just an instant before dissolving back into uncertainty. These quantum events, occurring millions of times every second within every atom of your body, form the hidden rhythm that supports all larger flows of time. When an electron shifts, a vibration occurs. When quarks exchange gluons, another tiny beat forms. In this sense, time does not exist independently. It rises from these countless microscopic transitions. As you let your thoughts drift through this quiet landscape, notice how the idea of time becomes softer, less rigid, more dreamlike. The clocks we build, the calendars we follow, the memories we hold, all of them rest on a foundation of delicate, shimmering events happening in silence below our awareness. In this deeper calm, the universe whispers something simple yet profound. Time is not something pushing forward from the outside. It is something created, moment by moment, by the gentle rearrangement of the smallest parts of existence. As we move further into the quiet architecture of atoms, the way time emerges becomes even more intricate. At this scale, almost nothing behaves like the solid, predictable motions we observe in our daily lives. Instead, time is woven from vibrations. Soft, repetitive, almost musical patterns that drift beneath the surface of matter, giving the universe its subtle internal rhythm. Every atom contains a signature frequency, a natural vibration that defines its identity. These vibrations are not physical shaking motions as we experience them, but oscillations in the probability fields that describe where electrons might be. When an electron occupies a particular energy level, it vibrates with a frequency unique to that state. When it moves to another level, that frequency changes. These transitions form the heartbeat of atomic time, small pulses of energy that fade gently across the quiet horizon of the quantum world. If you picture this on an unimaginably small scale, every electron in every atom around you, every atom in your skin, in the air, in distant stars, moves with a soft, repeating oscillation. These oscillations are incredibly stable, so stable that atomic clocks can detect them with astonishing precision. But beneath that stability lies an ocean of quantum uncertainty. Every vibration holds a slight unpredictability, like gentle waves shifting beneath dim light. It is this combination, precision wrapped around uncertainty, that gives atomic time its delicate balance. Inside the nucleus, the story becomes even more subtle. Quarks vibrate within protons and neutrons, held in place by the strong force. They do not rest. They drift in restless motion, flickering between states that cannot be pinpointed. Their fluctuations create internal patterns, tiny ripples of energy that contribute to the nucleus' sense of no. These ripples are so fast, so faint, that we cannot measure them individually. Yet collectively they shape the passage of time for the particle as a whole. When we observe an atom absorbing or emitting light, we are witnessing the creation of a tiny moment in this quantum rhythm. A photon, born from an electron shifting between energy levels, carries a packet of time with it, not in the sense of a ticking second, but as a record of a change that has happened. The universe marks time not by clocks, but by transitions. A particle fades from one state to another, and in doing so, the universe acknowledges that something has shifted. These transitions are the foundation of all timekeeping. A cesium atom, for example, vibrates at a frequency so steady that we define the second by counting its oscillations. Yet even this seemingly perfect stability is a graceful illusion. On the deepest level, quantum motion is irregular. Tiny deviations drift through the rhythm, softening its perfection. Atomic clocks correct for these deviations, smoothing them into a nearly flawless beat. But nature itself does not tick. It flows, it fluctuates, it breathes in patterns that hover between order and possibility. As you imagine these vibrations, endless, microscopic, shimmering beneath the surface of reality, notice how the flow of time becomes something almost poetic. It is not imposed on atoms from above. It arises from their quiet dances. Time is the consequence of transitions. the collective whisper of billions of quantum events unfolding in deeper calm. Beneath ordinary perception, these transitions fade into one another, forming the subtle threads from which all of time is woven. A key feature of atomic time is the quantum jump, an event that seems abrupt yet gentle, sudden yet smooth. When an electron shifts from one energy level to another, it does not travel through the space in between. It simply appears in a new state, as if space itself were skipping softly across a deeper rhythm. These jumps occur in silence, under a dim light of probability, and each one marks the birth of a tiny interval of time. Instead of moving continuously, nature moves in steps, quiet, delicate steps that drift between the possible and the actual. Every quantum jump is accompanied by a change in energy, and this change creates a ripple in the electromagnetic field. Sometimes that ripple becomes a photon, a small pulse that floats away carrying the signature of the transition. In this way, atoms do not just experience time, they generate it. Each photon is a record of a moment, a gentle wave sent outward into the universe, carrying information about what an atom has become. But the picture grows stranger. At the atomic level, particles do not act as objects moving in time. They exist as patterns, fields fluctuating in deeper calm. An electron's wave function stretches across space, describing not where it is, but where it might be. When it interacts with something, light, another particle, the environment, the wave function collapses, softening into a single outcome. That collapse is another kind of moment, the crystallization of possibility into reality. Inside the nucleus, quarks and gluons move so quickly, so chaotically, that assigning them a precise timeline becomes almost impossible. Their flickering interactions happen on timescales so short, they fall below the quiet horizon of measurement. Here, time itself seems granular, broken into fragments too small to feel. Instead of a smooth flow, the nucleus experiences something like quantum static, an ever-shifting sea of fluctuations where past and future blend, fade, and reform. Some researchers believe that these fluctuations represent the true essence of time, the tiny, ceaseless changes occurring everywhere, in every particle, in every direction. Time becomes not a single river, but countless microscopic currents flowing simultaneously. Each current is shaped by the frequency of a particle's vibration, by the transitions it undergoes, by the rhythms of the fields around it. In this sense, time is not absolute. It is relational, arising from the interactions of matter and energy. Even more intriguingly, when atoms move faster or experience stronger gravity, their internal rhythms slow, their vibrations drift, their transitions soften, and their sense of no changes. This is the essence of relativity. Time's flow depends on motion and gravity. At the atomic level, this means that two identical atoms, placed in different conditions, can live through time at different speeds. Their internal clocks tick differently, like gentle waves drifting apart on a vast sea. As we continue to unravel these small, fragile structures of time, we discover that the universe does not keep perfect time. It keeps personal time. Every particle carries its own rhythm, its own flow, its own quiet evolution. And from the intertwining of all these tiny rhythms, the larger river of experience emerges. The time we feel, the time we measure, the time we measure, the time we drift through every day. In this deeper calm, time begins to look like something alive. Not a rigid grid, but a soft field built from endless vibrations, endless transitions, endless gentle waves moving beneath the dim light of existence. As we move deeper into the quantum world, the idea of a clock begins to transform into something far more delicate than gears or ticking hands. At the atomic level, clocks are not physical devices but rhythms, patterns of vibration that drift softly beneath the surface of reality. Every particle in existence carries its own internal beat, a faint, almost undetectable oscillation that reflects how it experiences time. These tiny rhythms do not tick like mechanical seconds, but flow like gentle waves under dim light, forming a foundation for everything that unfolds in the universe. Each particle's mass determines its internal frequency. According to quantum theory, particles vibrate even when they seem perfectly still. These vibrations are astonishingly fast, far beyond anything we can measure directly. A single electron, for instance, oscillates billions of times per second, yet we never feel this motion. It happens far beneath our awareness, shaping the fabric of matter quietly, like a heartbeat hidden beneath layers of silence. These internal vibrations act as natural clocks, defining how a particle moves through time. Yet, despite their incredible precision, these clocks are not identical. When a particle moves faster, its internal rhythm slows. When it falls into a stronger gravitational field, the rhythm softens again, drifting into a slower beat. This is the essence of relativity expressed at the smallest scales. Time does not flow the same for everything, everywhere. Even two identical atoms drifting side by side can experience time differently if one moves slightly faster or sits a little closer to a massive object. Their frequencies diverge like gentle waves drifting apart across a quiet horizon. This phenomenon has been measured with exquisite precision. When scientists place one atomic clock on a shelf just a few centimeters higher than another, the two clocks fall out of sync, one running slightly faster than the other. The difference is tiny, but real. Height changes gravity. Gravity changes time. And time changes the atomic rhythm. This subtle shift reveals a profound truth. The flow of time is tied directly to the energy landscape through which atoms drift. Their internal beats fade or accelerate depending on the quiet curvature of space surrounding them. Inside every particle, energy states define a rhythm. In atoms, electrons transition between these states, creating pulses of electromagnetic radiation. These pulses, photons, carry information about how time unfolds within the atom. The clearer and more stable the transition, the better that atom becomes as a clock. This is why cesium-133, with its remarkably consistent internal rhythm, serves as the basis for our definition of the second. But even this perfect clock is only a soft approximation of nature's deeper complexity. Beneath its stable beat lies a shimmering chaos of quantum fluctuations, drifting in and out of sync with deeper calm. As we consider these internal rhythms, it becomes clear that time at the atomic level is not a smooth river. It is a layered tapestry woven from countless vibrating threads. Each atom carries its own beat, its own pattern, its own quiet motion through reality. When billions of these rhythms combine, they create the continuous flow we perceive as time. But when we peer closely, that flow fades into a collection of tiny intervals, each one marked by a quantum transition, each one softened by uncertainty. Even the concept of now becomes difficult to define. For a particle in superposition, existing in several states at once, there is no single present moment. Instead, there is a range of possibilities drifting through the quantum landscape, waiting to be shaped by interaction. Only when the particle interacts with its environment does one outcome crystallize, collapsing the spread of possibilities into a single moment we can recognize. That collapse is time taking shape, a gentle wave forming on the surface of the deeper calm beneath everything. Through these hidden clocks and subtle rhythms, time becomes less like a universal law and more like a soft negotiation between matter and motion. Each particle carries its own whisper of time, its own quiet heartbeat, contributing its own thread to the vast fabric of temporal flow. And as we continue this journey, it becomes clear that time is not simply passing. It is being constructed, moment by moment, by the tiniest motions in the quietest corners of the universe. As we drift further into the depths of atomic behavior, the boundary between time and energy begins to blur. In the quantum world, these two concepts are not separate entities. They are intimately connected, woven together like threads of a single tapestry. The more deeply we examine atoms, the more we realize that time is not simply something that flows, but something that emerges from the way energy is arranged and redistributed within matter. At the core of quantum mechanics lies the energy, time uncertainty principle. It tells us that the more precisely we know the energy of a system, the less precisely we can know its duration, and vice versa. This is not a limitation of our instruments. It is a fundamental property of the universe. Time and energy soften into one another, merging across a quiet horizon where certainty begins to fade. In the atomic world, exactness dissolves gently, allowing particles to drift through a range of possibilities rather than following strict, predetermined paths. Consider a particle that exists in a short-lived state. Because its lifetime is brief, the uncertainty in its energy becomes large. It flickers with unpredictable intensity, like a shimmering spark under dim light. These unstable particles appear and fade from existence in patterns that reveal the flexible nature of atomic time. Their fleeting presence is not a failure of stability, but a natural expression of the universe exploring every possible configuration. In more stable atoms, where energy levels are sharply defined, the flow of time becomes smoother. The transitions between energy levels create consistent frequencies, tiny internal rhythms that can be counted with precision. These rhythms form the backbone of atomic clocks, yet they remain connected to the deeper fluctuations beneath. Even the most stable frequency carries a whisper of uncertainty, a gentle wave of variation that drifts across the measurement. Inside atoms, energy is not a continuous spectrum, but a set of discrete levels. Electrons transition between these levels by absorbing or emitting photons. Each time a photon is released, the atom experiences a moment, a small, quantized shift that marks the passage of time in the most literal sense. When trillions of atoms undergo these transitions in synchrony, the collective effect becomes the measurable flow of time in our macroscopic world. What feels like a steady river is actually an ocean of tiny waves, moving in deeper calm. Yet beneath even these transitions lies something more mysterious. Energy itself is tied to the frequency of a particle's wave function. Higher energy means faster oscillation. Lower energy means slower oscillation. Thus, the internal rhythm of a particle determines its experience of time. A particle vibrating with higher energy lives through time more quickly relative to one vibrating with lower energy. But when motion or gravity intervene, these rhythms drift apart, revealing relativity not as a cosmic principle, but as a direct consequence of energy patterns at the smallest scale. This connection shows us something profound. Time, at its core, is a measure of change. Without change, time would not exist. A perfectly static universe would have no before or after, no transitions, no evolution, only stillness. But our universe is never still. Atoms vibrate, particles fluctuate, fields ripple. Everything is in motion, even in the depths of emptiness. These motions generate the flow of time, stitching moment to moment through the quiet actions of quantum energy. And so, as we imagine this landscape, dim, delicate, shimmering with possibility, we begin to understand that time is not a rigid framework holding the world together. It is a consequence of energy, reshaping itself endlessly. The universe does not move through time. It creates time with every quantum transition, with every vibration, with every fading and reappearing possibility. In this view, time feels less like a command and more like a whisper, a soft phenomenon emerging from the gentle waves of energy, drifting across the unseen spaces beneath reality, guiding the universe forward in deeper calm. As we continue sinking into the quiet architecture of the quantum world, the idea of time becomes less like a flowing line and more like a delicate texture woven into the energy fields that permeate reality. At this scale, nothing is solid, nothing is continuous, nothing is strictly defined. Instead, the universe reveals itself as a shifting landscape of probabilities, patterns that drift, overlap, and soften into one another under the dim light of pure possibility. Here, time takes shape not through movement, but through the changing patterns of these quantum fields. Quantum field is not a physical object, but a spread of potential that fills all of space. Every particle we know, electrons, quarks, photons, is simply a vibration, a localized ripple rising out of these fields. When the ripple appears, a particle exists. When it fades, the particle disappears. Even the appearance and disappearance are not single events. They are transitions, tiny steps through which time is created. Each ripple has a frequency, and that frequency anchors the particle in its own internal sense of time. Yet, these frequencies are never perfectly steady. They fluctuate, drifting with the uncertainties inherent to quantum mechanics. Even in absolute stillness, if such a thing could exist, quantum fields continue to flicker. This flicker is known as zero-point energy, the lowest possible energy a system can have. It is a soft, ever-present hum beneath reality, like gentle waves brushing against a quiet horizon. This constant motion means that even in the deepest calm, time is being generated moment by moment through transitions that never fully settle. This flickering nature leads to virtual particles, tiny, temporary fluctuations that appear and vanish too quickly to be observed directly. These particles live on borrowed energy, permitted by the uncertainty principle to exist for a moment before fading back into the field. Their births and deaths are not interruptions in time, but the foundation of it. Each appearance a new frame, each disappearance a soft merging with the next. Time at this level is not a stream. It is a sequence of quantum instants, stitched together by fluctuations too small to grasp. In this view, the difference between now and later dissolves. A particle may exist in multiple states at once, superposition blending possibilities into a single haze. Only when interaction occurs, when a measurement collapses the wave function, does one state crystallize, forming what we recognize as a moment. Before that collapse, time is undefined, drifting in a cloud of potential outcomes. After it, a direction emerges, as if a path suddenly appears beneath the particle's feet, guiding it gently into the next transition. Even entanglement, one of the strangest features of the quantum world, reshapes our understanding of time. Two entangled particles share a connection deeper than space itself. When one particle's state is determined, the other's state becomes fixed instantly, regardless of distance. This instantaneous correlation does not violate time. Instead, it shows how time itself is intertwined with information. The universe arranges its states in a way that transcends simple temporal order, softening the boundaries between cause and effect. These quantum behaviors suggest that time is not a universal rhythm, but a patchwork of local rhythms, each particle oscillating with its own frequency, each field fluctuating in its own quiet manner, each interaction creating a tiny anchor point in the unfolding of reality. When billions of these small rhythms blend, they form the smooth flow we experience. But beneath that smoothness, time is granular, delicate, full of small irregularities that drift beneath awareness. As we move further into this gentle landscape, it becomes clear that time is not imposed on the universe from the outside. It grows from within, from energy pulses, from wave collapses, from probabilities fading into actuality. Each moment is a consequence of change, a ripple moving through deeper calm, weaving the next instant into existence. And as these countless quantum transitions continue, softly, endlessly, The universe builds the illusion of continuous time, a quiet motion arising from the smallest waves under the faint glow of the dim light between moments. As we drift further into this silent architecture of the quantum world, we begin to reach a boundary where even the distinction between space and time starts to soften. At large scales, space extends outward, giving structure to distances, while time flows forward, giving structure to sequences. But deep beneath the atomic surface, these differences fade, dissolving into a single, intertwined fabric where neither exists on its own. In this dim light of quantum geometry, the two become expressions of something deeper, something woven into the very foundation of reality. Einstein's theory of relativity was the first to reveal this blending. Space and time, once treated as separate, are in truth two aspects of the same entity, space-time. Movement through space affects the flow of time. Movement through time influences how we experience space. At the everyday level, this relationship feels abstract, hidden, but at the atomic level, it becomes profound. A tiny change in energy, a small shift in position, a subtle variation in motion can ripple across an atom's internal rhythm, stretching or compressing time in ways too faint to notice yet too important to ignore. Consider an electron drifting in its cloud of probability. It does not occupy a single position. It spreads across space like a soft mist. At the same time, its internal frequency, a measure of its energy, guides its motion through time. But these are not independent qualities. The shape of the electron's probability cloud determines its energy, and its energy determines how quickly it moves through time. Space influences time. Time influences space. The two are bound together like gentle waves shaping each other beneath a quiet horizon. At even smaller scales, this unity becomes more dramatic. When particles interact, they exchange energy, and with that exchange comes a shift in space-time curvature. Even a single photon, faint and weightless, can slightly alter the geometry of the space it passes through. On cosmic scales, gravity bends light around stars, creating elegant arcs across the sky. But at atomic scales, these effects drift silently beneath awareness, adjusting the passage of time in minuscule increments. Every exchange, every vibration, every fluctuation shapes time's pace in a subtle but real way. Time dilation, the slowing of time due to speed or gravity, also applies at the atomic level. When atoms move faster, their internal oscillations slow, drifting into a lower frequency. When placed deeper into a gravitational field, their rhythms soften even more. Two identical atoms, separated by just a few centimeters of height, will experience time at slightly different rates. While the difference is tiny, it reminds us that time is not universal. It is local, shifting with the energy and curvature of the space-time around each particle. At the deepest layer of this landscape lies an idea even more subtle. That space-time itself may not be fundamental. Instead, it may be something that emerges from quantum processes. Some theories suggest that space and time arise from the entanglement between particles, that the connectivity of quantum information creates the geometry of the universe. In such models, space-time is not a stage on which quantum events unfold. It is a consequence of those events. The fabric of reality is formed by relationships, by correlations, by the soft weaving of information across countless quantum states. In this perspective, time becomes a measure of how entanglement spreads, how systems move from order into uncertainty, and how probabilities collapse into definite outcomes. Every quantum interaction stretches this web, creating a new configuration of space, a new slice of time. The universe does not evolve in time. It creates time through its own quiet transformations. As we rest in the stillness of this idea, it becomes clear that space and time are not rigid directions, but soft dimensions, shaped by motion, energy, and information. They fade into one another like gentle waves, merging under the dim light of a deeper calm. The boundaries between where and when blur, revealing a reality that is more fluid, more interconnected, and more dreamlike than we ever imagined. And through this soft unity, we begin to see that the flow of time at the atomic level is not separate from the shape of space. It is carved by it, woven through it, drifting quietly within the endless fabric beneath everything. As we drift deeper into the quantum landscape, a profound truth unfolds. The universe at its smallest scales does not operate through certainty, but through probability. And because of this, time itself becomes a probabilistic phenomenon, something that does not move with strict precision, but instead with a gentle, fluctuating rhythm. Time at the atomic level is shaped not by rigid sequences, but by the shifting likelihood of events, the fading in-out of possibilities, and the quiet transformations that soften reality into its next state. Quantum probability is not randomness in the chaotic sense. It is structured, guided, and deeply mathematical. The wave function, which describes a particle's state, holds all possible futures for that particle, its potential positions, energies, and interactions. These futures exist simultaneously, layered in a haze of possibility. When a measurement occurs, the wave function collapses, selecting one outcome. That collapse is the birth of a moment, a small crystallization of reality at the quiet horizon, between what might happen and what does. This collapse does not reflect time moving forward. It creates the sense of forward movement. Each collapse becomes a stepping stone in the timeline of a particle. Between collapses, time has no definite meaning. It drifts in a space where nothing is fixed. Only when probability fades into a definite event does a moment form, stitching together the flow of experiences we call time. Inside an atom, these collapses happen constantly. Electrons transition between energy levels. Quarks flicker in and out of temporary configurations. Photons appear and fade as they carry information across space. Each event is a small quantum decision, a selection from a cloud of possibilities. Billions of such decisions occur in every moment of your existence, weaving together a continuous experience from countless microscopic choices. Even the stability of objects around you, the solidity of a table, the glow of a screen, the air moving softly around you, depends on these probabilities maintaining their delicate balance. Electrons remain near nuclei because their wave functions create stable probability distributions. Molecules form because the probability patterns describing shared electrons settle into harmonious shapes. Nothing is fixed. Everything is a quiet agreement among probabilities, drifting in deeper calm. Because probability governs events, time behaves differently in different quantum situations. A particle with a wide range of possible energies experiences time differently from one with a narrow range. Unstable particles, whose probabilities fade quickly, live fast, blinking into and out of existence in extremely short intervals. Stable particles, whose probabilities are tightly defined, flow through longer spans of time. Their internal clocks drift more slowly, echoing the steadiness of their states. Even more gently, quantum tunneling, where a particle appears on the other side of a barrier without crossing it, shows how probability shapes time. The particle does not move through space in the traditional sense. Instead, the probability of its presence gradually increases on the far side of the barrier until it becomes real. The moment it becomes real is the moment time catches up to the particle's new state. Time, in this sense, is tied not to motion, but to the emergence of certainty from uncertainty. This is why the flow of time can feel different depending on the stability of systems. Unstable atoms decay according to probability distributions, not clocks. Radioactive decay is not timed by an internal mechanism, but by a probability curve. Each atom waits for a collapse, its moment drifting through a quiet haze until the configuration shifts. The decay time is not an appointment. It is a likelihood that grows gently until a change occurs. As we imagine this probabilistic universe, we see time not as a rigid script, but as a soft unfolding. A gentle wave moving through layers of possibility, a dim light flickering softly between what is real and what is allowed to be real next. A deeper calm shaped by the subtle rearrangement of probabilities drifting across the quantum world. And it becomes clear that the flow of time at the atomic level is not predetermined. It is negotiated, moment by moment, between all the possibilities the universe allows. As we continue drifting through the delicate interior of the quantum world, a subtle but powerful idea begins to come into focus. Without measurement, time does not unfold in a definite way. At atomic scales, the universe does not experience a clear sequence of events the way we do. Instead, it exists in a soft haze of possibilities, where change is not a continuous flow, but a potential waiting to be shaped. Only when interaction or observation occurs does that potential fade into a single outcome, creating a moment, an anchor point in time. In the quantum realm, measurement is not simply the act of looking. It is any interaction that forces a particle to reveal one of its possible states. When an electron interacts with a photon, when a molecule bumps against another molecule, when a particle is struck by a passing wave, a process unfolds in which the spread of probabilities collapses into a definite result. This collapse forms the microscopic equivalent of now. Before the collapse, the particle drifts through a cloud of potential. After the collapse, it stands briefly in certainty, and during the next instant, the cloud forms again. This pattern, potential, collapse, potential, creates the rhythm of time at the atomic level. Time becomes a sequence of transitions rather than a continuous motion. Each collapse marks a step forward, but between collapses, the arrow of time becomes blurred, softened into possibility. It is as though reality breathes, inhaling potential, exhaling clarity, drifting between the two with a rhythm we cannot perceive directly. One of the most striking examples of this is the famous double-slit experiment. When electrons pass through two slits without being measured, they do not choose a single path. Instead, they behave like waves, spreading out, floating through both paths simultaneously, creating an interference pattern. Their motion does not follow a clear timeline. It fades into overlapping possibilities. But when we measure which slit an electron travels through, the wave function collapses. The electron chooses a path. A definite moment emerges. Time becomes anchored. Why does measurement create time? One interpretation is that information plays a fundamental role in defining the order of events. When a particle's state is uncertain, its temporal evolution is not fixed. There is no definite past or future, only probability. But when the environment gathers information about the particle, such as through a collision or a beam of light, the particle becomes entangled with that environment. The entanglement locks the particle into a state, and that locked state becomes part of the universe's timeline. This idea suggests that the universe does not passively flow through time. Instead, it constantly selects, decides, and organizes itself through countless tiny acts of measurement. At every moment, interactions between particles create new layers of certainty, shaping the progression of time with each quiet collapse. And each collapse sends gentle waves of information through the fabric of space-time, helping define the sequence of events that follows. Even your body, your breath, the atoms drifting through your cells are doing this continuously. The electrons in the molecules of your nerves are collapsing into definite states as they interact with one another. Photons emitted from your surroundings scatter off your skin, off your eyes, creating new moments. Each interaction builds your personal experience of time from the inside out. This perspective softens the boundary between observer and universe. At the atomic level, observation is not a conscious act. It is simply interaction. Every collision, every exchanged photon, every shifting field creates a moment, and the sum of these moments becomes the temporal fabric through which atoms, molecules, and eventually conscious beings drift. In this deeper calm, the flow of time becomes less like a river and more like a gentle sequence of ripples, each one forming when uncertainty fades, each one drifting softly beneath the dim light of measurement, each one helping shape the quiet horizon of what happens next. As we move deeper along this quiet path through atomic time, we encounter one of the most mysterious and beautiful principles in all of physics: entanglement, a phenomenon where two particles share a connection so deep that their states become inseparable. In this realm, the flow of time is no longer something experienced by one particle alone. Instead, it becomes a shared rhythm, a soft pulse linking distant pieces of the universe in a single, elegant motion. When two particles become entangled, their properties intertwine. Their energies, their spins, their probabilities drift into a common structure, as if they share a unified clock ticking beneath the dim light of quantum possibilities. What happens to one affects the other instantly, regardless of the distance between them. They do not communicate across space. They are the same information, stretched across a quiet horizon where time and separation soften into something more fluid. This shared structure reveals that time, at its smallest scales, is not an individual experience. It is relational. A particle's no can become fused with another's now, creating a single coordinated moment. When the wave function collapses for one particle, a collapse occurs for its entangled partner as well. One event can define the moment for both, stitching together a fragment of time that spans across space like gentle waves reaching two distant shores. This phenomenon defies our classical understanding of time. In everyday life, information moves at finite speeds. Causes precede effects. But in the quantum realm, entanglement bypasses these limitations. It does not violate causality. It simply exists outside the normal flow. The shared state of entangled particles is not carried through time. It is established before time begins to unfold for them. Their connectedness lies deeper than temporal order, resting in a calm layer beneath the measurable flow. To understand how this shapes the atomic experience of time, imagine two electrons created together in a single event. They drift apart. One moves into the chill vacuum of space. The other remains close to a warm atom. Their environments differ. Their energies shift. Yet the underlying connection remains. When a measurement collapses one electron's wave function, the other's possible states fade instantly into a corresponding condition. From our perspective, this looks like information moving faster than light. But from the quantum perspective, the two electrons never truly separated. They are different expressions of a single state, drifting through deeper calm. Entanglement also affects how time spreads through larger systems. In atoms, electrons can become entangled with one another, creating coordinated rhythms. These rhythms influence chemical reactions, energy transitions, and the stability of molecules. Even the structure of proteins, the behavior of enzymes, and the firing of neurons can involve quantum correlations that drift beneath our ordinary experience of time. Life itself may rely on these quiet, coordinated rhythms humming softly under the dim light of biological processes. Another remarkable consequence is the possibility that space-time itself arises from entanglement. Some theories suggest that the geometry of the universe, the distances, the curvature, even the very notion of continuity, emerges from the pattern of quantum correlations. Massive networks of entanglement may create the scaffolding upon which space and time unfold. In this view, time is not a background stage. It is the result of information being shared, transferred, and collapsed across quantum connections. This perspective dissolves the idea of time as a single universal river. Instead, time becomes a tapestry woven from countless interactions, with entanglement acting as the threads that tie its pieces together. Each collapse of a wave function becomes a small ripple. Each quantum connection stretches that ripple outward, and the universe evolves not through an external clock, but through the soft merging and fading of possibilities across a network of shared states. As we rest in this understanding, it becomes clear that entanglement is more than a curiosity. It is a quiet engine beneath the flow of time, a whisper connecting particles, a rhythm synchronizing distant states, a gentle wave drifting across the unseen fabric of reality. And within this deeper calm, time itself unfolds not as a solitary line, but as a shared, interconnected motion, moving beneath the quiet horizon of existence. As we drift even further into the quiet interior of the quantum world, we reach one of the most remarkable human creations, the atomic clock, an instrument built entirely on the delicate motions we have been exploring. These clocks, the most precise ever invented, reveal the hidden structure of time by listening to the faintest vibrations of atoms drifting in deeper calm. They do not rely on gears or springs. Instead, they measure the gentle waves of quantum transitions, turning the quiet flicker of electrons into the steady heartbeat by which we define seconds. At the core of an atomic clock is an atom with an exceptionally stable frequency. Cesium-133 is the most famous example. Its electrons shift between two energy levels with such perfect regularity that the transition can be used as a universal reference. When an electron changes its state, it emits or absorbs radiation at a frequency so precise that counting these oscillations allows us to measure time with unimaginable accuracy. 1 second is defined as the duration of exactly 9,192,631,1770 of these oscillations. A rhythm so steady that it drifts only a fraction of a second over millions of years. But beneath this astonishing precision lies the same quantum softness we've been tracing. Each oscillation emerges from a probability cloud, not a fixed motion. The vibration is stable, not because nature is rigid, but because the quantum world, despite its uncertainty, settles into patterns that fade gently into equilibrium. The electrons drift through these patterns like waves lapping under dim light, returning again and again to the same frequency as though guided by a quiet horizon buried deep within the atom. The beauty of atomic clocks is that they expose the subtle influence of relativity at incredibly small scales. Lift an atomic clock just a few centimeters higher, and it runs slightly faster. Lower it, and it runs slower. Even the gentle pull of Earth's gravity is enough to soften or tighten the rhythm of atomic transitions. Time itself bends to the landscape of space-time, shifting its flow in a delicate interplay between motion, energy, and position. These variations may seem insignificant, but they accumulate. GPS satellites, for example, orbit Earth far above the surface, where gravity is weaker. Their clocks run faster, about 38 microseconds per day, than clocks on the ground. Without correcting for this drift, GPS would quickly become useless. The fact that we must adjust for atomic-level time dilation proves that time is not absolute. It is flexible, shaped by the quiet curvature of space-time, revealing its structure through these soft, gentle discrepancies. More advanced atomic clocks, built from ytterbium or strontium atoms cooled to near absolute zero, reach even deeper precision. These atoms vibrate at higher frequencies, forming finer ripples across time. In some experiments, clocks made of these atoms detect differences in time flow over distances smaller than a millimeter. This means that time is flowing at slightly different speeds at the top and bottom of your body, your desk, even the thickness of a page. Time is not uniform. It drifts with height, with motion, with energy. It is woven into the gravitational and quantum textures of reality. Yet among all this precision lies a poetic truth. Even the most perfect clock cannot measure time itself. It measures change, the shifting of energy levels, the transition from one quantum state to another. Time emerges from these changes, not the other way around. In the atomic clock, electrons fading between energy states create the ticking. In the universe, countless particles shifting in endless transitions create the flow of time we feel. There is no separate river of time behind the scenes. There is only the quiet rhythm of change, generating moment after moment. And as we reflect on this, a calming perspective unfolds. The entire experience of time, every second, every minute, every drifting memory, is built from the tiniest motions, the softest vibrations, the deepest calm hidden beneath reality. The same gentle waves that guide atomic clocks also guide the unfolding of stars, the formation of galaxies, and the quiet rhythm of breath in your chest. Time is, and always has been, the universe learning how to transition from one moment to the next. As we drift deeper into the hidden architecture of time, we reach a concept that shapes everything we experience, from the cooling of a star to the way memories form in the mind. The arrow of time. Unlike the reversible rules of quantum mechanics, the arrow of time points in one direction only, from past to future. It is gentle yet unbreakable, shaped not by the behavior of individual atoms, but by the collective unfolding of enormous numbers of them, drifting together in deeper calm. At its heart lies entropy, the measure of disorder. While quantum events allow particles to move backward or forward in time, the macroscopic world, our world, follows a quiet tendency toward increasing disorder. Ice melts, stars exhaust fuel, warm things cool, memories form but do not reverse. This slow, inevitable fade from structure into randomness creates the familiar flow of time we sense. It is not a push from the past, nor a pull from the future, but the soft settling of possibilities into likely outcomes, like gentle waves stretching across a quiet horizon. On the atomic level, each event is reversible. An electron can jump up or down an energy level. A particle can scatter and recombine. A quantum wave can evolve backward just as easily as forward. But when billions of such events combine, their collective motion becomes overwhelmingly likely to follow one direction, towards states with more randomness. This statistical tendency becomes the arrow of time, emerging from the sum of microscopic shifts, even though no single microscopic step requires it. Imagine a drop of ink drifting into water. Each molecule moves randomly, guided by collisions and thermal motion. At the atomic scale, nothing demands that the ink spread outward. It could, in principle, reassemble into its original form. But the number of configurations in which the ink is mixed is vastly greater than the number in which it remains concentrated. And so the drop fades gently into the water, softening into a uniform blue under the dim light of diffusion. This process illustrates how time's direction emerges, not from strict laws, but from overwhelming probability. Entropy also shapes the formation of structures. Stars form when clouds of gas collapse under gravity, concentrating matter into hot, bright cores. At first glance, this seems like a decrease in disorder, but the heat released during collapse increases the entropy of the surrounding environment, ensuring that time's arrow remains unbroken. Even creation, star birth, crystal formation, biological growth, unfolds along pathways that ultimately increase the universe's overall disorder. The arrow of time is woven into every quantum transition as well. When an atom emits a photon, the photon drifts outward, carrying energy with it. Although the process could be reversed in principle, the photon's escape creates a spread of information, that cannot easily be gathered again. The universe expands the space of possibilities, allowing energy and information to fade outward like ripples softening into deeper calm. On cosmic scales, entropy drives the evolution of the entire universe. In the early moments after the Big Bang, matter and energy were tightly packed into a uniform, low-entropy state. As the universe expanded, new possibilities opened. Stars ignited, galaxies spun, particles combined into atoms. And with each transformation, the arrow of time grew stronger, guiding the cosmos into a future rich with complexity and motion. Even the decay of unstable particles is shaped by entropy. An atom with high internal energy is more likely to transition into a lower energy state, emitting a photon or pulsar. Each decay event contributes a tiny push to the arrow of time, adding to the gentle waves that drift across the quantum landscape. For us, the arrow of time is inseparable from experience. Memories exist in one direction. Causes precede effects. The warmth of a moment fades gently into the past. This flow feels smooth, natural, inevitable. Yet it emerges from countless microscopic decisions, from probabilities settling into new configurations, from interactions drifting through deeper calm. And so, as we rest in this understanding, the arrow of time becomes not a rigid force, but a soft inclination, a gentle tilting of reality toward the future, shaped by the universal tendency of systems to expand into possibility, like light slowly dissolving across a quiet horizon. As we drift further into the quiet mechanics of time, a profound truth begins to reveal itself. Time does not flow at the same speed for everything. At the atomic level, clocks made from the steady rhythms of electrons do not always tick in perfect unison. Their frequencies soften or tighten depending on how fast they move or how deep they rest within a gravitational field. This gentle bending of time, known as time dilation, is one of the most beautiful consequences of Einstein's relativity, and one that shapes the entire universe from the smallest atoms to the largest galaxies. Imagine two identical atoms, both vibrating with the same internal rhythm under dim light. If one atom begins to move faster, perhaps drifting through space or falling toward a massive star, its internal frequency slows. The clock inside the moving atom ticks more slowly relative to the one at rest. This soft stretching of time is not a mechanical effect, but a geometric one. When an object moves quickly, some of its motion must be allocated to space, and the remaining portion is left for time. As speed increases, the flow of time fades gently, leaving the moving particle with fewer moments per second. On Earth, this effect is subtle but measurable. Atomic clocks carried aboard airplanes run slightly slower than identical clocks left on the ground. Even the small difference in velocity changes the rhythm of electrons, causing their oscillations to drift. When the clocks are compared afterward, the discrepancy reveals the quiet truth. Time is not absolute. It is shaped by motion, softened by speed, stretched by the path a particle follows through spacetime. Gravity plays an even more profound role. A clock placed deep within a gravitational well on the surface of a planet, near a massive star or close to a black hole, ticks more slowly than one placed farther away. Gravity curves space-time, and this curvature affects the pace of time's flow. The deeper the gravity, the slower the rhythm. Even just raising a clock by a few centimeters lifts it into slightly weaker gravity, causing it to tick faster. At human scales, the difference is too small to perceive, but atomic clocks reveal the subtle drift with extraordinary precision. This gravitational time dilation shapes the entire cosmos. In the intense pull of a black hole, time slows so dramatically that an outside observer sees objects fade into stillness. A particle drifting toward the event horizon appears to move in deeper calm, its transitions stretched until they become nearly frozen. For the particle itself, time feels normal, but for the outside universe, its clock softens into near silence. This dramatic contrast shows how time is not a universal river, but a flexible fabric shaped by mass and motion. Even in everyday life, your body experiences slight variations. The atoms in your feet, closer to Earth's center, tick more slowly than the atoms near your head. The difference is unimaginably small, but real. If you lived for billions of years, the top half of your body would experience slightly more time than the bottom. It is a reminder that time flows differently depending on height, motion, and gravitational pull, weaving a subtle gradient through every moment we experience. These effects extend through the universe. Near massive stars, time flows more slowly, causing their light to drift toward the red end of the spectrum. In the expanding cosmos, galaxies racing away from us experience time differently from nearby stars. Even within the swirling jets around black holes, particles experience wildly varied flows of time depending on their distance from the center. The universe is a patchwork of temporal landscapes, stitched together by relativity, softened by curvature, drifting across a quiet horizon shaped by gravity. But perhaps the most comforting realization is this: despite the differences in how time flows, every region, every particle, every atom experiences its own timeline naturally. There is no correct speed of time. Each clock drifts in harmony with its surroundings, like gentle waves settling into a larger ocean. And from the merging of all these individual rhythms, the slowed beats near massive objects, the quicker pulses in empty space, the universe creates the vast and beautiful complexity of its evolving story. Time in this view is not a single pulse but a symphony of rhythms, each softened by motion, each drifting across the dim light of gravity, each carrying its own whisper of deeper calm.